Okay, so now when your variable is in the exponent, you need to use logarithms to unlock the exponent. Now, you could use the common log here if you wanted, but since the base is e, I strongly recommend that you use the natural log. The reason being, what can I do with this x now? It's one of the rules of logarithms. You can bring it down in front. And the natural log of e, and the reason you want to use the natural log when the base is e, is that the natural log of e is 1. So I'm left with x equals the natural log of 18, which equals approximately 2.890. (24). E to the 2x equals 10. Base e, I'm going to apply the natural log. Bring the 2x down in front. And when I bring the 2x down in front, like I did here, what am I left with? What should I write next? I'll write it one more time. Natural log of e equals the natural log of 10. Natural log of e is 1. So dividing by 2, I get x equals the natural log of 10 divided by 2. Not the natural log of 5, the natural log of 10 divided by 2, which equals approximately, in 24, 1.151. (25). E to the x plus 1. Gabby. Go ahead. E to the x plus 1 equals 30. To unlock the exponent, I need to apply the log. I'll apply the natural log because the base is e. Bring the x plus 1 down in front. Why didn't I write x plus 1 times the natural log of e? Because the natural log of e is 1. Equals the natural log of 30. X equals the natural log of 30 minus 1. Not the natural log of 29, the natural log of 30 minus 1, which equals approximately, in 25, 2.401. (26) says e to the x over 5 plus 4 equals 7. Before I can apply the natural log, I need to get this stuff by itself and everything else over here. In other words, subtract 4 from both sides, and I get e to the x over 5 equals 3. Now I can apply the natural log. Then I can bring the x over 5 down in front, leaving me the natural log of e, and the natural log of e is 1. So I'm left with x over 5 equals the natural log of 3. X divided by 5, I undo that by multiplying each side by 5. And I get x equals 5 times the natural log of 3, which is approximately 5.493. So far, so good? Wow. Gabby? How I'm just dropping e? On your calculator, you got a calculator there? Punch in the natural log of e. What do you get? One. So back up here where I was writing it, do you agree with me I can bring this x down in front? So I have x times the natural log of e. In all of these, I end up with the exponent times the natural log of e. Now here I stopped writing it. Why did I stop writing it here? Because every time I'm ending up with a natural log of e. And the natural log of e is 1. Do I need to write that 1? No. So that's why the e is disappearing. That's why I like the natural log. Because the natural log of e is 1 and makes my calculation, frankly, easier than when we were using the common log. Can I go on to 27? Super duper. 27. E to the 2x equals 12. To unlock the variable that we're solving for out of the exponent, I need to apply a logarithm. I'm going to apply the natural log because e is my base. If I apply the logarithm to one side, I need to apply it to the other side. By applying the logarithm, the power of that is I can bring that down in front, and I end up with 2x times the natural log of e equals the natural log of 12. That equals 1. So I can divide each side by 2, and I get x equals the natural log of 12 divided by 2, not the natural log of 6, the natural log of 12 divided by 2, and that equals approximately 1.242. Let me do 28, and then we can answer questions. 28. E to the x over 9 minus 8 equals 6. Shh. Before I can apply the logarithm, I need to get everything else on the other side. In other words, add 8 to both sides. E to the x over 9 equals 14. Now I can apply the natural log. Now I can bring that exponent down in front. And I'm not going to write the natural log of e because we know it's 1. To undo the 9 here, I need to multiply each side by 9, and I get x equals 9 times the natural log of 14, which equals approximately 23.752.